Next, we are going to look at the reactions of esters. One of the first reactions of esters that we're going to talk about is the hydrolysis of esters. This is the reaction of esters with water. And when an ester reacts with water, okay, so when an ester undergoes hydrolysis, what happens is the ester is converted to the carboxylic acid and the alcohol that constituted the ester. Now, the hydrolysis reaction can be accomplished or can be done under different conditions. It could be either acidic or basic. We'll look at them one by one. Under acidic conditions, an ester is reacted with acid, aqueous acid. So that means we have H plus acid and there's water, okay? And with heating. So we can basically represent the H plus and the water by using H3O plus, like a hydronium ion. And so the ester is converted into the carboxylic acid plus the alcohol. Now, notice that this is the reverse of a Fischer esterification reaction that was also done under acidic conditions, and it converted the carboxylic acid and the alcohol into an ester molecule. So the hydrolysis under acidic conditions is just the reverse of a Fischer esterification reaction. We'll look at the mechanism of this reaction, which is basically the reverse of a Fischer esterification reaction. So the mechanism of the reaction starts with an initial protonation or a proton transfer. And like any other carboxylic acid derivative or any other reaction involving carboxylic acids, the proton transfer or the protonation occurs at the acyl oxygen. The acyl oxygen is what gets protonated. So in presence of an acid, the acyl oxygen gets protonated. So electrons are pushed up to that oxygen. And we will get the protonated ester molecule. So we get the protonated ester where the acyl oxygen has been protonated. And along with this, we make water. And realize this reaction is going on under aqueous conditions, so there is enough water around. Once you get the protonated ester, the second step here is the attack by water on the protonated ester molecule that opens up that pi bond or the double bond onto the oxygen atom. And it would give us a hydroxyl group here, give us a water molecule that's connected to that carbon, has a formal charge on that oxygen, and there is OR prime group here, okay? So the R prime. Now, if you look at the products, what we need to do is we need to break this bond between that carbon, the acyl carbon and the ester oxygen. We need to break that bond. And so we'll have to like protonate it at some point. But right now, the most immediate thing that we're going to do in the mechanism is to deprotonate this. So again, under these reaction conditions, water would be the most ideal base that's present here. So a molecule of water, another molecule of water can deprotonate that hydrogen. So electrons go to that oxygen and we get a molecule where there are two hydroxyl groups connected to it, and then the OR prime. Now, if you go back to the mechanism of Fischer esterification, you would notice that we arrived at a similar intermediate in that mechanism also. In fact, all of these intermediates should bear some resemblance to what we saw in the Fischer esterification mechanism. Okay, once you're at this intermediate, along with this, you've made acid again. So the hydronium ion is regenerated. And now any of these oxygen atoms in this intermediate can get protonated. If the hydroxyls get protonated, they bring us back. But whenever this oxygen, the ester oxygen gets protonated, that takes us forward in terms of the mechanism of the reaction. So it will take us to the next step where we have RC hydroxyl group, OR prime, OR prime, and there is a hydrogen here, one lone pair and one positive charge. And at this point, the the alcohol, the protonated alcohol that we've created here, that can be pushed out. It is a good leaving group. Okay, we've converted the bad leaving group, which is an alkoxy group, into an alcohol good leaving group. So one of these oxygens, the hydroxyl oxygens, would push down its lone pairs, and that would assist in the loss of this alcohol group. So those electrons come down and the alcohol is lost. So it will bring us to the next intermediate, where we have R, we have C double bond O, OH with a protonated acyl oxygen. And along with this, we will have the alcohol molecule. So we've created the alcohol molecule now, the R prime OH. And in the last step then, in the last step here, another molecule of water, which is present in excess here, that can come and deprotonate this oxygen to give us the carboxylic acid plus H3O plus. So if you notice, overall, we've converted the ester into a carboxylic acid and the alcohol, so the products that we've drawn here. And we've added overall like a molecule of water in that process. So that's the mechanism of an ester hydrolysis under acidic conditions. Next, we're going to look at hydrolysis under basic conditions. So under basic conditions, the hydrolysis of an ester is done in two steps. You initially react the ester with a base. I'm using sodium hydroxide, a very classic base here. And so when you do this reaction, the ester reacts with your base to give you a carboxylate ion and then an alcohol. And then in the second step, you do a hydrolysis, like an acidic workup actually. So an acidic workup here. And when you do that reaction, you convert this carboxylate ion into the carboxylic acid, and the alcohol was already there. So to convert this carboxylate into the carboxylic acid, an acidic workup is needed, or a protonation step is needed. Let's look at the mechanism of this reaction. Now, since this is a reaction that's going on under basic conditions, the mechanism would resemble the mechanism of or the reactions of carboxylic acid derivatives under nucleophilic or basic conditions here. So let's work on the mechanism here. So the mechanism starts out with the attack by the nucleophile on the acyl carbon. So there is no protonation here. There is no initial protonation. The mechanism starts out by the attack of the nucleophile here, which is your hydroxide, on the acyl carbon. Attacks the acyl carbon, the double bond here is pushed up, and that would give us RC minus with a hydroxyl group to it and an OR prime. So you get the tetrahedral intermediate, okay? That's the tetrahedral intermediate. And from the tetrahedral intermediate, you can now get the collapse of the tetrahedral intermediate. So the negative charge comes down, and as it comes down, in principle, it can push out the hydroxyl group here as a hydroxide, and that would bring us back. Or it could push out the alkoxide group. That would take us forward. So we will get the carboxylic acid, okay, the C double bond O, OH, plus you're going to get R prime O minus, that's an alkoxide, okay? This oxygen here, that becomes the alkoxide. Now at this point, if you notice, we have the carboxylic acid and the alkoxide, but the carboxylic acid is more basic than the carboxylate, okay? So what happens is once you get here, so there is an acid-base reaction and the alkoxide deprotonates the carboxylic acid to give us the carboxylate ion plus the alcohol. So all of this happens in step one. And that's why at the end of step one, you end up with a carboxylate ion and an alcohol, because this acid-base reaction is favored in the forward direction. So it's not so favored in the backward direction because the carboxylic acid is a stronger acid compared to the alcohol here, or the alkoxide is a stronger base compared to the carboxylate. Okay, either ways, it is favored in the forward direction. So you end up with the carboxylate ion, and so that's why when we do this second step, which is the acidification, okay, or we do an acidic workup. Now the carboxylate gets protonated so that we get a carboxylic acid molecule here. So we generate the carboxylic acid that way. We have already generated the alcohol. So in the end, essentially, we have the carboxylic acid plus the alcohol. This basic hydrolysis of an ester, okay, or the hydrolysis of an ester under basic conditions is also called a saponification reaction. It's called the saponification reaction. And that's because this reaction is used to make soaps, or it was used to make traditional soaps starting from vegetable oils. We're going to draw that scheme next. Soaps were traditionally synthesized by the saponification reaction of esters. But these esters are specific molecules. They are triglycerides, okay? These are the molecules that make up vegetable oil or animal fat. So the molecule of vegetable oil or animal fat looks like this. Now it's drawn in a very weird way, sort of, but if you look at it, there are 3 ester groups in this molecule, okay? So it is basically a molecule with 3 ester functional groups, and the alcohol that is here is glycerol. That's why these are called triglycerides. So when you take triglycerides, which are basically vegetable oils or animal fats, and you react them with sodium hydroxide as a base, excess of the base, because we have 3 ester groups here, what happens is you end with the alcohol here, okay, which is glycerol. You get glycerol. So each of these is a carbon, okay? This is a bond line structure for that molecule, essentially. You could draw it differently, but you have 1, 2, 3 carbons with a hydroxyl group on each one of them. That's glycerol. Plus, under these conditions, as we saw, we get the carboxylate ion. So you're going to get 3 molecules of carboxylates. And since we are using sodium hydroxide, these would be sodium salts. So even here, we are using sodium hydroxide. So this carboxylate would have a sodium ion attached to it, or bonding to it with an ionic bond to it. Okay, what's specific or what's special about these esters is that the R group here, okay, this R group is a long carbon chain, okay? And depending on the oil or the fat that you're using, they could be 10 carbons or longer, up to like 20, 22, 24 carbons, okay, depending on what vegetable oil or animal fat you're using. Now, for some of the more common vegetable oils, so for example, olive oil or like palm oils, these carbon chains or the R group here, that can be a total of like 15 or 17 carbons, because they usually have about 16 to 18 carbons, and that includes this carbon, the acyl carbon. So the R group itself is about 15 to 17 carbons. But these molecules, sodium salts of these carboxylic acids, these are used as soaps, or at least traditionally, these were the soap molecules. Now we have other methods which allow us to make soaps, but they still maintain a similar structure or like some similarity with the structure. Okay, so the saponification reaction is useful for making soaps, a direct application of this chemistry here. Next, we are going to look at the reaction of esters with hydridic reagents or hydride reagents, like lithium aluminum hydride. When an ester is reacted with excess lithium aluminum hydride followed by an acidic workup, our product is an alcohol. In fact, we make two alcohols here, okay? And I'll walk you through that. Why? Okay, so essentially what happens in this reaction is the acyl carbon here, that is reduced, okay? That's the reduction. The carbon-oxygen double bond is gone. So that's reduced to an alcohol here. So the acyl carbon becomes the alpha carbon for one of the alcohols, but the ester has another alkoxy group in it. That comes out as the second alcohol. So overall, you're getting two alcohols from this reaction. Now, most often and very often, you focus on the alcohol that's coming from the acyl part of it, because the other molecule here was already very close to an alcohol. So the reduction is for the acyl carbon. Let's look at the mechanism of this reaction. It is very similar to the reaction of lithium aluminum hydride with acid chlorides and acid anhydrides. So the mechanism starts with an initial attack by lithium aluminum hydride on the acyl carbon. So we're going to use aluminum hydride here. So one of these nucleophilic hydrides goes and attacks the acyl carbon. The double bond gets pushed up. And again, this is a nucleophilic reagent, so our mechanism resembles the reaction of carboxylic acid derivatives, or resembles the nucleophilic acyl substitution under nucleophilic or basic conditions. So the first step is an attack. Electrons move up, so we get our carbon with a single bond to an oxygen. We have OR prime, and we've got a hydrogen on that carbon. And along with this, we're going to have our aluminum, okay, with the three hydrogens on it. Now, after this, like any other nucleophilic acyl substitution reaction, this is our tetrahedral intermediate. So the tetrahedral intermediate collapses, the oxygen brings down its lone pairs, and at the same time, the alkoxide group here is kicked out, that leaves. Now, hydrogen is a very bad leaving group, so that does not leave in this particular step. And this takes us forward to the next intermediate, where we're going to have an aldehyde, KRC double bond O with an H, plus we have an R prime O minus, an alkoxide that came out, okay? So this is one of the alkoxides that we made in this process. We're going to leave it there, but we're going to track it later. Now, we have excess lithium aluminum hydride, and what we know is that aldehydes also react with lithium aluminum hydride. So the reaction doesn't stop. In fact, if you try to stop it at the aldehyde, it would not work. You will get a mixture of products. So it's better to just let it continue on. So this reacts with another molecule of the hydride. The hydride comes and attacks now the carbonyl carbon, okay? We started with an acyl carbon. Now we have a carbonyl carbon. So the hydride from the lithium aluminum hydride comes and attacks the carbonyl carbon. That will bring us to this intermediate, which is notice another alkoxide. Okay, so we made another alkoxide here. So this is alkoxide 2. Number 2, alkoxide number 2, along with we have the aluminum reagent. Now, in principle, okay, you can use all 4 hydrides in the lithium aluminum hydride, but for the sake of mechanism, we're showing separate aluminum hydrides to work through the mechanism here, okay? So that's basically the first step. And notice, by the end of this first step, we have 2 alkoxides in our reaction now, okay? We have alkoxide 1, which was present in the ester, so that's the OR group in the ester, and we have alkoxide 2, which is from the acyl carbon. So this carbon here is the reduced acyl carbon. And now, when we do the acidic workup here, okay, when we do the acidic workup, the alkoxide here will get protonated, but there is enough acid simultaneously that other alkoxide is also going to get protonated. So when we do this reaction, at the end of it, we're going to have 2 alcohols in our reaction. We'll have alcohol from alkoxide 2. We will also have the alcohol from alkoxide 1. Okay. Now, like I said earlier, in most cases, you track the alkoxide that's coming from the acyl carbon, because that's the carbon which is reduced. So that's the one that we usually focus on. Let's look at a quick example here. So let's say if we have an ester like that, methyl benzoate, if we reduce it with lithium aluminum hydride excess followed by an acidic workup, we will get 1 alcohol from this alkoxide in the ester, or the alkoxy group in the ester, and we're going to get another alcohol that corresponds to this acyl carbon. So our reaction will give us 2 alcohol products. One will be benzyl alcohol. This carbon, the acyl carbon, is reduced to an alcohol, and plus it will give us methanol. Now, since we are doing a reduction here, the benzyl alcohol here, that would be considered our reduced product. Okay, we are not doing a reduction as far as this methoxy group is concerned. So we're not doing a reduction as far as the OR prime is concerned. We're doing a reduction of the acyl carbon. So this would be our main product. Okay, that's something important to keep in mind. So we looked at the reduction using lithium aluminum hydride, which helps us convert esters into alcohols, or the acyl carbon in an ester into an alcohol carbon. What if we wanted to stop at the aldehyde and not go further? How would we do that? We're going to look at that next. Now, a reagent that is useful in converting an ester to an aldehyde, and again, I want to mention that when we say ester to an aldehyde, we are referring to the acyl carbon. That's what we are focusing on. So if you look at the scheme here, the acyl carbon, which is a carboxylic acid derivative here, okay, is converted into the aldehyde here. So to convert an ester to an aldehyde, a reagent that's useful is DIBAL-H, okay, DIBAL-H, which is diisobutyl aluminum hydride. This is the structure of DIBAL-H. So there are two isobutyl groups on the aluminum along with one hydride. The mechanism of this reaction is very similar to that of a lithium aluminum hydride mechanism, except that you will use DIBAL-H instead of the aluminum hydride. But the advantage to this reaction is that if you react an ester with DIBAL-H, this reaction is done at low temperatures. Okay, so that's important. If you do this reaction at low temperatures and you follow it up with an acidic workup, you're able to isolate the aldehyde. You can stop at the aldehyde without over reduction to the alcohol. Because with lithium aluminum hydride, what happens is the aldehyde product gets further reduced to the alcohol. So we are able to avoid that reduction here and isolate an aldehyde. Again, notice that the alkoxy group in the ester here still becomes an alcohol, but that is not what we're focusing on. We're focusing on the acyl carbon. We're talking about the reduction of the acyl carbon, and the acyl carbon here, which is a carboxylic acid-based carbon, is only reduced as far as a carbonyl compound. So we can stop at the carbonyl compound. So depending on what you want to do with the ester molecule, whether you want to reduce it completely to an alcohol or to an aldehyde, or you want to stop at the aldehyde, you can choose an appropriate reagent. If you want to reduce an ester completely to an alcohol, you use lithium aluminum hydride. If you want to reduce the ester to an aldehyde, you would use DIBAL-H. Those are the two reagents that make these reactions possible. The reaction of esters with organometallic reagents, specifically a Grignard reagent, is very similar to those of all other carboxylic acid derivatives. When an ester reacts with a Grignard reagent and you use excess of the Grignard reagent followed by an acidic workup, what happens is the ester, again, we're talking about this acyl carbon in the ester molecule, that gets converted into a tertiary alcohol. We get a tertiary alcohol here. And plus, the alkoxy group becomes another alcohol group as usual, but we're focusing on the acyl carbon. So the acyl carbon here becomes the tertiary, the alpha carbon in the tertiary alcohol. It gives us a tertiary alcohol. The mechanism here is very similar to the mechanism of the Grignard attack on an acid chloride or an anhydride, which goes through the intermediacy of a ketone. So you first convert your ester into a ketone, and then the ketone is further reacts with the Grignard reagent to give you the tertiary alcohol following the acidic workup. Let's look at an example of this reaction. So if we start with an ester, and again, I'm going to use methyl benzoate here as an example. If we take methyl benzoate and if we react it with ethyl magnesium bromide, an excess of it followed by acidic workup, the acyl carbon here is going to become the alcohol carbon. So we'll still have the benzene ring. Acyl carbon becomes the alcohol carbon, and we'll have two ethyl groups connected to that carbon. So that gives us the tertiary alcohol product along with this methoxy group here becoming the methanol. But our focus here is on the acyl carbon, so that gets converted into the tertiary alcohol here. So that's the reaction of esters with Grignard reagents, which helps us convert an ester into a tertiary alcohol. I hope you find all of these reactions and the discussions useful. Bye.